Debye-Huckel theory of strong electrolytes. Before going to detailed discussion of this theory, let's discuss some of its introduction. And as we have discussed earlier, that the equivalent conductance increases with dilution in case of weak electrolytes. So equivalent conduction increases with dilution. That was for weak electrolytes. This increase in the equivalent conductance of the weak electrolytes can be explained using Arrhenius theory. And this theory suggests that the conductance increases because the dissociation of weak electrolyte increases with dilution. So why that increase is due to the increase in dissociation of weak electrolytes due to dilution. For example, at lower concentration, the number of acetate and hydrogen ions generated from the acetic acid in aqueous solution, greater the number of ionic species that are generated from the molecular species or the acidic species, that is undissociated form, and these are the dissociated form. Greater the number of these ionic or dissociated species, greater will be the dissociation that increase with increase in dilution. So that was the case for the weak electrolyte. So now let's discuss about the strong electrolytes. Strong electrolytes are usually completely dissociated at any concentration. That's why the sign of unidirectional reaction is shown for the dissociation of the strong electrolyte, whereas for the weak electrolyte, the number of ionic species that are dissociated from the molecular species are in equilibrium with each other. So the strong electrolytes are completely dissociated even at moderate concentrations. So for strong electrolytes, the increase in equivalent conductances for such electrolytes with dilution may be due to the other factors. So this theory, known as Debye-Huckel theory of strong electrolytes, explore those factors which increase the conductance of strong electrolytes on dilution. So here we get the Debye-Huckel theory explains the factors which increase the conductance of strong electrolytes on dilution. And what are those major factors? So the first one is relaxation effect or asymmetry effect, and the second one is electrophoretic effect. Now let's discuss the first factor, that is the relaxation effect or asymmetry effect. Electrolytes, when dissolved in solvent, then electrolytes dissociated into solution state to give positive and negative ions. For example, when sodium chloride is dissolved in water, the sodium ion is surrounded by the chloride ions, whereas chloride ions are surrounded by sodium ions. So each ion is surrounded by an ionic atmosphere of opposite charges, and this arrangement of the opposite charges that is surrounding to each ion is known as ionic sphere, and ideally this ionic sphere must be symmetrical, which means that the number of ions that are surrounding this central ion must have equal distribution around space. Now let's take an example. Here we have a central positive ion that is surrounded by a symmetrical, that is slightly symmetrical with counter ions, and when a current is passed through the solution with application of current to the two oppositely charged electrodes, the center of or the central ion of the ionic sphere moves towards the oppositely charged electrode. During this movement, it has to rebuild an ionic atmosphere of opposite charge around this central ion that is moving towards the oppositely charged electrode. At the same time, the older ionic sphere dies out that was symmetrical. So the breakdown of the symmetrical ionic sphere and formation of new asymmetric ionic sphere are not simultaneous. There is some time lag which is called the time of relaxation. During this time, old ionic atmosphere pulls the moving ion backward, so its motion is retarded with the application of the current to the electrodes, and due to this relaxation effect, that is the requirement of time between the resolution of this older ionic sphere and formation of new ionic sphere, and the older ionic sphere retard its motion so that it can reach to the electrode surface and conduct current. So the number of oppositely charged ions that are reaching to the oppositely charged electrode surface are lower as compared to the expected value, so that's why the expected value of conductance couldn't be reached. So there is a time lapse between the resolution of the older ionic sphere and formation of new ionic sphere, and this time lapse is known as relaxation effect, and something can be explained in another way. When the central ion moves of this ionic sphere that is left behind having an excess or the effective negative charge as compared to this positive ion that is moving towards the negative electrode, so the effective charge or the effective excess ions that are making an atmosphere that is present behind this moving positive ion pull up this positive ion so that the motion of this ion towards the negative electrode is retarded, making the number of these positively charged ionic species that are reaching to the negative electrode are decreased with respect to time. So in this second explanation, in which we have a asymmetric ionic sphere or the excess ionic charge that is surrounding this moving positive ion, pull up this positive ion and retard its motion. So this effect is also known as asymmetry effect. So relaxation is the time lapse between the breakdown of this symmetrical ionic sphere and formation of new sphere, and asymmetry effect is the formation of the asymmetrically distributed counter ionic sphere, that is the excess charge that pull up the positive charge towards themselves to make its motion retarded in the direction of the negative electrode. The second reason behind the decrease in the conductance of the strong electrolytes with dilution is the electrophoretic effect that is explained using this figure. So during the application of electromotive force, the central ion moves in one direction and the oppositely charged ions present in their ionic atmosphere moves in opposite direction towards the oppositely charged electrode. For example, for this figure, positive ions are actually moving towards the negative electrode, and these negative charges that are making the asymmetric ionic pair around this positively charged ion are actually moving towards the positively charged electrode in opposite direction. And solvent molecules are also there in the ionic atmosphere. It means that the central ion is moving against the stream. So when these ions are dissolved in this water, so the negatively charged, that is the partial negative oxygen that is surrounding this positively charged sodium ion. So here this sodium ion or the positive ion is also surrounded by the solvent molecules. So similarly, the negative ions are also surrounded by the solvent molecule, that is water. So for this case, the hydrogen that are partially positive part of the water molecules are showing the attraction towards this central negatively charged ionic species. So in this way, the partially positive or partially negative ends of the water molecules are attracted towards the either positive or negative ionic species. So here we can see that the red dots are showing the solvent molecules. So during the application of the electromotive force, the central ion moves in one direction and the oppositely charged ions present in their atmospheric sphere move in opposite direction, and the solvent molecules are also there in the ionic atmosphere. It means that the central ion is moving against this stream. Hence, the motion of this central ion is retarded. This retardation effect is known as electrophoretic effect. And here we have the medium that is represented as dots that are the of the central ion in opposite direction to that of the ionic atmosphere. and that of the associated molecules. And whenever an ion with ionic atmosphere travels in the solution, then the medium of the solution offers the frictional resistance. This force depends upon the viscosity of the medium and its dielectric constant. So the frictional resistance, or the force that is in opposite direction to the movement of the ionic species, are the function of the eta, that is viscosity of the solution, and dielectric constant, which is also known as relative permittivity. Now come to the mathematical explanation of the Debye-Huckel theory. So keeping the three factors, number one is relaxation effect or asymmetry effect, the second one is electrophoretic effect, and the third one is the frictional resistance of the medium. So keeping these three factors in view, Debye-Huckel developed a mathematical expression given here in 1923, and actually they derived relationship by keeping in view the variation of the equivalent conductance with the concentrations. So here the concentration is given in the square root. The equation derived by Debye-Huckel is given here in a modified form, and the equation derived by the Debye-Huckel theory was further improved by the Onsagar in 1926. So the equation is actually known as Debye-Huckle-Onsagar equation. So the equation given here is actually the modified form of the Debye-Huckel equation. And if the electrolyte is univalent like sodium chloride, potassium bromide, known as univalent electrolytes, then the equation is given as follows, where capital copper is showing the equivalent conductance at any concentration, and lambda naught is showing the equivalent conductance at infinite dilution. D is the dielectric constant of the medium. Eta is the viscosity of medium, whereas T is the temperature of the solution. And the most important variation is the concentration of solution in moles per decimeter cube, that is changing with respect to the equivalent conductance. So here C is the concentration of solution in moles per decimeter cube. If we observe this equation, which is known as Debye-Huckle-Onsagar equation, in this equation the values of the dielectric constant, temperature of the solution, and viscosity of the medium are the constant parameters for a given concentration of the solution. So for this reason we can put the encircled parameters as constant values. So for this purpose this encircled value is a constant A, and this one is a constant B. So this Debye-Huckle-Onsagar equation have been modified or simplified through this equation. And in this equation we can see that the value of the equivalent conductance at infinite dilution is always higher than the equivalent conductance at any concentration, which is subtracted value of the equivalent conductance at infinite dilution with this factor, which is shown in the brackets and the square root of the concentration. So the equivalent conductance is always found to be less than the equivalent conductance at infinite dilution, and this is due to the both asymmetry and electrophoretic effect. And the first term in the brackets, that is A, refers to the electrophoretic effect, which is inversely related to the viscosity of the medium. And the second term given by this equation is a measure of asymmetry effect. So the constant A is the measure of electrophoretic effect, and the constant B is the measure of the asymmetry effect, which are subtracted from the total amount of the equivalent conductance at infinite dilution, so that the value of the equivalent conductance at a particular concentration is less than this equivalent conductance at infinite dilution. So at infinite dilution, according to the equation given by Debye-Huckle-Onsagar equation, when solution is infinitely dilute, then the value of the concentration approaches to zero. So when the concentration approaches to zero, the zero value multiplied to these terms will give the value of the contribution that is negligible. So the value of equivalent conductance at infinite dilution, when the concentration of the solution is approaching to zero, this value is approximately equal to the equivalent conductance at infinite dilution. So what does it mean? It means that the factors A and B are responsible to create a difference between this conductance and the conductance at infinite dilution. So the greater the concentration, greater the factor A and B that are contributing to the equivalent conductance, and the greater deviation from the lambda naught, which is equivalent conductance at infinite dilution. So when concentration of the solution is increased, that led to significant contributions of the constant A and B in this equation, that is subtracted from the equivalent conductance at infinite dilution. As a result, decrease in the value of equivalent conductance is observed. Now let's check out the experimental verification of the Debye-Huckle-Onsagar equation. And here if we plot a graph between equivalent conductance, that is in ohms per ohm centimeter square per gram equivalent, versus square root of the concentration as given by the equation. Here we have the value that is plotted at x-axis against the value that is plotted at y-axis, and the intercept at the y-axis will give the value of equivalent conductance at infinite dilution, which is usually calculated through extrapolation of the plots that are obtained by varying the concentration of the solution and measuring the equivalent conductances. And in this plot we have taken the examples of the univalent electrolytes. It means that the valency of the positive and negative ionic species is +1 or -1. So the plots are shown here are a straight line which are obtained at very dilute solution. From here we can see the concentration in the square root is given here we have 0.08 the square root, but the concentration of the solution is actually very dilute. So these straight lines are following the Debye-Huckle-Onsagar equation are actually at very dilute concentrations. When we use higher concentration, the deviation from these straight lines will be observed. That led to the formation of curved lines with higher concentration of the solutions. So here we can see that by increasing the concentration of the solution, there is a decrease in equivalent conductances from the conductance at infinite dilutions. So these points are showing the equivalent conductances of these electrolytes at infinite dilution, which is extrapolated at zero concentration. Now let's discuss the experimental demonstration of the migration of ions. So in order to investigate the movement of ions under the influence of applied electrical field, we take up the arrangement as described here. So let's take a tube that is U-shaped and fill it with the agar-agar jelly. And introduce the solution of copper sulfate and potassium dichromate, which generate the solution of copper sulfate and potassium dichromate will make the copper chromate solution that is green in color, which convert the color of jelly that is 5% agar-agar to green colors. This agar-agar jelly is actually a non-conductive porous medium, that is a polymer, which provide a porous channel for the movement of the ions present in the porous microscopic channel of this jelly. After this green colored jelly that is obtained by the uniform distribution of copper chromate within the pores of this jelly, there are two limits. In order to discriminate the boundary of the jelly that is in green colored, some charcoal is scattered over the green jelly to make the positions of the jelly distinctive, and then potassium nitrate solution is allowed to set in agar-agar jelly at the surface of this scattered charcoal layer. And finally, potassium nitrate solution is placed over the agar-agar jelly containing potassium nitrate solution, and this solution is connected to the external circuit through the introduction of these two electrodes. Now when the current is applied to the system as shown here, so what happened? The copper plus 2 ions having blue color seems to move towards the negative electrode. At the same time, yellow colored chromate ions move towards the positive electrode, and we get well defined two new boundaries that are defined by the plain agar-agar jelly and the blue copper ions, as well as yellow dichromate ions, and this boundary was already marked with charcoal. So using this kind of experiment we can measure the properties relevant to the migration of ions with application of the electric field.